In this video, we'll be looking at model evaluation using leave one out cross-validation, and we'll illustrate that with a bivariate dataset and 6 data points. So when we have very few data points, it's going to be challenging for us to separate the data out into a test set and a training set. And so we need to come up with another way by which we can validate and evaluate our model. For the purposes of illustration, we'll consider 3 different models. One's the linear model, then we have a quadratic polynomial, and then a piecewise linear function. If we were not doing any model evaluation and fit all the data, then of course we can come up with the sum of squared errors. But this is not enough because we really don't know how well these models will generalize to new data. So this brings us to leave one out cross-validation. So what we're going to be doing is we are going to be selecting 5 out of the 6 points to be our training data, as you can see in the picture. And one of the points, the first point, is going to be our test data. We then fit our models to the training data. We have the linear, quadratic, and piecewise linear functions. And we evaluate our fits against the test data, and using the residuals we can come up with the squared error for each one of these 3 models. We keep this aside and we repeat this exercise for the other data points. So now we're going to be choosing the second data point to be our test point and the other 5 points to be our training data. We fit our models and evaluate them against the test data point. Again, we get a squared error. We repeat this with the third data point being our test data point. Then again, with the fourth data point being our test data. And then the fifth data point being our test data, with the remaining 5 points being our training data. We repeat this for the sixth point as well. So if we have 6 data points, we're going to be doing 6 model evaluations, as you can see over here, with the linear model, and the average squared error over all of these 6 folds is computed. Finally, we have the quadratic polynomial and the averaged square error. And finally, we have the piecewise linear function and the corresponding squared error. Now, we make a comparison between each one of these 3 models in terms of their average squared errors. We can see that the quadratic polynomial gives the best fit across each one of the 6 different test data points. And so it's a model that fits the data well and generalizes to new data too. So here are some key points as far as leave one out cross-validation is concerned. We use each data point exactly once as test data. And in general, we use leave one out cross-validation when we have small data sets. It does get computationally expensive when you have very large data sets. As you recall, we had 6 data points. So for each one of the models, we had to fit 6 different models. So we had 6 different linear fits, 6 different quadratic polynomials, and 6 different piecewise linear functions. So just to make the choice of the best model in amongst these 3, we had to do 18 different model fits. Now, of course, in practice, we would be evaluating 6 or 7 different models, and in general, the data sets are going to be a little bit more complex, and so you can imagine that this could potentially be computationally expensive for very large data sets. So it's suitable for smaller data sets, and if you do have large data sets, then it's best to use k-fold cross-validation.